first unit of CA 301 strength of materials 1, that is stress, strain and deformation of solids. Contents to be covered: elastic constants, composite bars and thermal stresses. So first let us see the elastic constant and the relationship. So there are totally 4 elastic constants and that we are using for studying the elastic behavior of different materials. The first one is Young's modulus of material, Poisson ratio, bulk modulus and shear modulus. So these 4 elastic constants are using. And let us see, first one is the Young's modulus. So as we have already discussed the Young's modulus, as per the Hooke's law, stress is directly proportional to strain within the elastic limit, strictly speaking up to limit of proportionality. Therefore, sigma is directly proportional to epsilon, or sigma is equal to E into epsilon. Here we use a constant, so where E is equal to Young's modulus of the material, and therefore E can be defined as the ratio between stress and strain. Okay. E is equal to, that is Young's modulus of that material, is equal to stress divided by strain. Next, Poisson ratio. So this Poisson ratio of material, the symbol is used in nu or 1 by m. So in which let us take a prismatic solid of dimension L, then B, then D, along x direction, y direction and z direction. Yes, there is a stress sigma x along the x direction only. So here uniaxial stress is applied in this bar. There is a solid bar which is subjected by a uniaxial force tension sigma x only along the x direction, and therefore uniaxial force, there will be an uniaxial stress along x direction, that is sigma x. The strain along x, that is epsilon x, is equal to sigma x by E. So because Young's modulus is equal to sigma x divided by epsilon x, and therefore epsilon x equal to sigma x by E. This is strain subjected along x direction only. Now, so because of this pulling occurs along the x direction, what happen? The lateral direction or along y direction and the z direction, what happen? You see that this is the d initial dimension, whereas after the body is subjected by pull, what happen, or it is elongated, the depth d gets reduced. You see that the depth d decreases, and also simultaneously breadth also decreases. So these two shortening of length occurs due to a tension force acting along the x direction. So if there will be a linear strain, so because of that linear strain, what happen? The lateral dimension decreases, so laterally it is strained. Yes, so that is given here. So strain along y direction, strain along this y direction along the lateral, epsilon y is equal to minus nu into epsilon x. So this strain is determined in terms of the linear strain, that is minus nu into epsilon x, like that. The strain along z direction, that is epsilon z, so this will be the z direction along breadth. So here also dimension decreases, and therefore there is strain, and that epsilon z is equal to minus nu into epsilon x. It is also equal to minus nu into epsilon x, where nu is the Poisson ratio. So the Poisson ratio can easily be defined as nu is equal to minus epsilon y divided by epsilon x, or is equal to minus epsilon z divided by epsilon x, which is equal to minus lateral strain divided by longitudinal strain. So here put sign minus means, so because of this uniaxial direction strain, that is linear strain, the strain occurs laterally is opposite to this linear strain. So this minus denotes opposite to the direction of strain is opposite to the linear strain. So that is denoting this minus. So now as per this discussion, the Poisson ratio can be defined as the ratio between lateral strain and longitudinal strain. So it is unitless parameter. Next, shear modulus or modulus of rigidity. So here we use the symbol N or sometimes C or G. So shear modulus can be defined as the ratio between shear stress and shear strain. So this is another elastic constant. So we have so far we have discussed Young's modulus and Poisson ratio. So there is some other elastic constants. So the next one is shear modulus. Shear modulus can be defined as the ratio between shear stress tau and shear strain gamma. So let us see how the shear strain is being determined. So let us take this object ABCD. There is a plane ABCDE which is distorted due to this shear tau as A, B dash, C dash and D dash. This is distorted figure. Here the plane is affected by shear stress. How can we ascertain? So in this case the right angle at 90 degree, initially there is right angle at A is 90 degree, which is suffered due to this distortion. Okay, this distortion, and this suffered 90 degree is due to pi 1 and pi 2. So that is the sheared angle, or that will be the strain. Thus the change was measured by suffering the right angles as shear strain. Therefore the total shear strain gamma is equal to pi 1 plus pi 2, which is equal to B dash divided by AB, then is equal to plus D dash divided by AD. So these are nothing but the strain or angle pi 1 and pi 2. Therefore gamma, pi 1 and pi 2 are in radians. Yes. So like that we can find the shear strain. Shear stress is the given stress tau. So now from which we can find the shear modulus, that is shear stress divided by shear strain. So next, bulk modulus. Bulk modulus can be defined as the ratio between direct stress and volumetric strain. Okay, so if an object is subjected by direct stress or linear strain, and there will be direct stress sigma is equal to that P divided by A, and also we have to find out the volumetric strain for that object due to this uniaxial stress or uniaxial strain, from which we can find the K is equal to sigma divided by epsilon V, where epsilon V is equal to volumetric strain. Yes. Then next let us see the relationship between elastic constants, that is K, E and nu, that is bulk modulus, Young's modulus and Poisson ratio. So in which we go for a cube which is immersed in a large depth of water. Then the water pressure on cube P is equal to sigma x equal to sigma y is equal to sigma z is equal to sigma. So as per Pascal's law of transmissibility, the pressure at any points on the water is evenly distributed in all directions, and therefore P becomes pressure P is equal to or stress equal to sigma x, sigma y is equal to sigma z is equal to sigma, like that. Then epsilon x equal to, that is strain along x direction, is also equal to epsilon y, which is equal to epsilon z, which is equal to epsilon. And therefore if I want to find the epsilon x or epsilon y, epsilon z or any epsilon which is equal to sigma by E, that is linear strain along one direction, sigma by E, minus strain along lateral direction, one direction, that is nu into epsilon by E, minus strain along another direction, epsilon divided by E, which is equal to the the total strain on that material due to linear strain, which is equal to epsilon by E into 1 minus nu, 2 nu. Therefore, the volumetric strain can be calculated, that is epsilon V is equal to epsilon X plus epsilon Y plus epsilon Z. In this case, epsilon V is equal to 3 into epsilon, since the cube immersed in water, and therefore 3 epsilon. Therefore, K is equal to, we can come from this, we can find K is equal to sigma divided by epsilon V, which is equal to sigma divided by 3 epsilon. Here volumetric strain is equal to epsilon X plus epsilon Y plus epsilon Z. Therefore, total volumetric strain is equal to 3 epsilon, which is equal to sigma divided by the 3. We know epsilon is equal to sigma by E into 1 minus 2 nu. So that E comes to numerator, which is equal to E divided by 3 into 1 minus 2 nu, from which we can find E is equal to 3K into 1 minus 2 nu. So this is one relationship between elastic constant. So next, the relationship between shear modulus N, Young's modulus E, and Poisson ratio nu. So it is now related to sigma and tau as well as gamma and epsilon. So here also we have to assume that there is a plane or there is an object which is subjected by pure shear in all directions, and therefore in that case, when it is subjected by pure shear, the normal stress, the maximum normal stress in that plane becomes sigma, that is tau becomes sigma. Normal stress is also equal to tau. Yes, then maximum normal stress in that direction, in that plane, in that case becomes sigma, and the gamma is directly related with the linear strain, that is shear strain is directly related with the linear strain, which is nothing but gamma is equal to 2 into epsilon x. Okay, then epsilon x is nothing but linear strain, which is equal to sigma by E into 1 minus nu, 1 plus nu. Therefore, sigma by 2 into E divided by sigma into 1 plus nu, which is equal to E divided by 2 into 1 plus nu, and therefore E is equal to 2n into 1 plus nu. This is another relationship between elastic constants, and from like that we can also derive algebraically with the use of the above two relationship or two elastic constant relationship. So here one is E is equal to 3k into 1 minus 2 nu, and another one is E is equal to 2n into 1 plus nu. So when we algebraically combine these two, we have another relationship, E is equal to 9kn divided by 3k plus n. These are all the some relationship between elastic constants. Yes. Then problem solved in this area. So the following data relate to bar subjected to a tensile test. Diameter of the bar D is equal to 30 mm. Tensile load P is equal to 54 kN. Gauge length L is equal to 300 mm. Extension of the bar del L is equal to 0.112 mm. Change in diameter del D is equal to 0.00366 mm. Then calculate Poisson ratio, the values of 3 moduli. So from this, so these are all the test data are taken from the tension test on steel rod. Yes, let us find first Poisson ratio. In which Poisson ratio, the relation is to find Poisson ratio nu is equal to lateral strain divided by linear strain. So here, in order to find the lateral strain, we have let us go step by step. First, let us find the direct stress. Direct stress sigma is equal to, because they are giving the tensile load P is equal to 54 kN, and then we know the diameter of the bar, that is equal to 30 mm, 30 mm, 30 mm, and therefore area, first let us find the area, and then P by A is giving the direct stress for this. And next let us find the linear strain. By knowing this stress, linear strain is equal to del L by L. Here the extension of the bar is directly given, and we know the gauge length of the bar, that is L is equal to 300 mm, and therefore let us substitute in, and we have the linear strain. Then lateral strain epsilon del D by D, also there is given change in diameter, that is lateral elongation or lateral shortening, which is equal to 0.00366, and this is the original dia 30, therefore we have the lateral strain. Now from which we can find Poisson ratio nu is equal to lateral strain divided by linear strain. Yes, so we have 0.327. This is nothing but Poisson ratio. Then next, the values of 3 moduli E, C and K. E can be found using the relationship stress by strain. That is, we know that stress, and we have already calculated strain, therefore E is equal to, the relationship that we know, E is equal to 2C into 1 plus nu or 1 plus m. Therefore from which we substitute E divided by 2 into 1 plus 1 mu 1 by m, and therefore let us substitute this all value, we can find the value of C. And another one is E is equal to 3k into 1 minus 2 nu or 1 minus 2 by m. 3k E is equal to 3k into 1 minus 2 nu or 2 by m, and therefore from which we can find k. K is equal to 1.97 into 10 power 5 meganewton per meter square. Yes. So next let us see the composite bars. A member consisting of two or composite bar is nothing but, it is also an object or a bar consisting two or more parallel elements of equal length but of different materials rigidly fixed with each other, that behaves as one unit and subjected to axial loads, is called a composite bar. So there are different materials, there are different bars made with different materials, but both are interconnected and acting as a single unit, that is called as composite bar. So in that case, we just apply the axial load, and this material is being used some other purpose in engineering field. So in that case, we apply some load on the member, that is this composite member or composite bar, and it will be shared by the various components of the section. Suppose let us apply P, a force. So this total force is shared by the materials which are used to manufacture this composite bar. So composite bars are analyzed based on the following assumption. First, the extension or contraction of each element is equal. So the extension or contraction of each element is equal, that is, the deformation per unit length or strain in each element is equal. So the total strain in that composite bar is also equal to the strain in one material, that is a bar or a member which is made with one material, and the another bar is also in there. So both strain are equal. The total load on the composite section bar is equal to the sum of the load carried by each part of that material or each element of that material. Let us see. This thing is explained in this illustration. Here we have a column. Column is to be considered as a composite member because it consists a concrete column, and inside of the column the rods are also being used to carry this P. Okay, P, axial force P. So this column made up of with a concrete as well as steel. So both are acting as single unit, therefore it is a composite member. Here AC, EC and PC are the area of cross section, modulus of elasticity and load shared by concrete respectively. Like that, AS, ES and PS are the area of cross section, modulus of elasticity and load shared by steel respectively. So let us take like this, and then strain in this composite member, epsilon is equal to sigma by E. Here, so as per the assumptions of composite section, we know that epsilon C is equal to epsilon C, that is strain in concrete is equal to strain in steel, which is equal to total strain, and therefore this strain epsilon C can be written as sigma C by EC. We know that EC is equal to sigma C by epsilon C, and therefore this epsilon C can be written here sigma C by EC, which is equal to this epsilon S equal to sigma S by ES. So let us use this is, let us take as equation number 1. So from which we can write sigma C in terms of sigma S, that is sigma C is equal to sigma S into EC by ES, or sigma S equal to sigma C into ES by EC, where here ES by EC is nothing but the ratio between Young's modulus of steel and Young's modulus of concrete, which is called as modular ratio of that material. So now we know that ES and EC, that is Young's modulus of steel and Young's modulus of concrete for this material. Concrete we know, and for steel it is also the data given from which we can find sigma S in terms of sigma C, or sigma C we can find in terms of sigma S. The next part, the total load P is equal to PC plus PS. What is PC? That is load carried by concrete portion, and PS load carried by steel portions. So sum of these two, which is nothing but the total force acting on this column. Therefore P is equal to, again this is force can be here substituted as sigma C into AC, that is stress into area, which is nothing but force. Stress into area, because stress equal to load by area or force by area, in which therefore force equal to stress into area. P is equal to sigma C into AC plus PS equal to like that sigma S into AS. Yes, that's all. So we know that area of individual member or individual material, here used cross sectional area of the individual material, that is area of concrete and the area of steel. So this thing we know. Now let us substitute that one, and we just substitute sigma C in terms of sigma S, and already sigma S here, from which we know the total force, from which we can find sigma S. So by knowing sigma S and substitute here, we can find sigma C. So from which we can find the force carried by individual. So now we know sigma C and sigma S, and we know area of the individual material. Let us multiply with the stress into that corresponding area of that material. Here stress in steel into corresponding area of the steel material, steel section, and therefore now we obtain force shared by individual material. That's all. So like that we can find the force shared by individual material using these steps. So this is the common procedure adopted for finding the load shared by individual material of composite bar. Next, let us see the temperature effects. So when temperature of a material changes, there will be a corresponding change in dimension. Here any material or any member should be subjected by the temperature stresses and temperature strain and temperature stresses. So like that. So because of that effect of temperature, how can we find the temperature strain, temperature stress? So let us see that part in this area. So when temperature of a material changes, there will be corresponding change in dimension. Yes, it may be expanded or it may be shortening. If the difference in temperature, these things are happen. So temperature stress are induced only if the deformations are prevented. Yes, so once if the member is freely allowed, there will not be any stresses induced. But if the members are clamped or its deformations are prevented, then the stresses, thermal stresses or temperature stresses are subjected. First, let us see how we can find the temperature strain in the given member or material. That is, epsilon is equal to temperature strain, epsilon is equal to alpha into T. What is alpha? Alpha is nothing but coefficient of thermal expansion of the material. T is nothing but change in temperature. So now by knowing this strain, from which we can find what is the deformation on that member due to this temperature or this thermal effects, temperature effects. That is change in length of member delta L is equal to, if we know strain, then original length into epsilon. Therefore alpha T is strain into L, which becomes the, we can find the change in length of that member due to temperature effects. Therefore temperature stress, by knowing strain, then stress is nothing but strain into Young's modulus. Okay, so we know that strain is alpha T and Young's modulus is E, therefore sigma is equal to E alpha T, where alpha is equal to coefficient of thermal expansion of the material, T is equal to change in temperature, and E is equal to Young's modulus of the material. So like that we can find the temperature strain, then change in length due to this temperature strain, and also we can find the temperature stress due to that temperature strain we can find in a material. You see that what is the thermal stresses in compound bars. So the compound bars means already we have discussed, it consists of two or different materials and acting as single unit. So let us have that compound bar or composite bar, in which it is also subjected by temperature effects, and therefore two different metal bars A and B, if both are rigidly connected, both will be subjected to common deformation. Let alpha A and alpha B their coefficient of thermal expansion. So there are two materials A and B. Let alpha A be the coefficient of thermal expansion of the material A, and alpha B is the coefficient of thermal expansion of the material B. In this case, if alpha A is greater than alpha B, that is, this is material A has more thermal expansion value, coefficient of thermal expansion value, than material B, in which due to temperature fall, in that case the change in temperature is reduced with respect to standard temperature of that material, and therefore part A is, that is material, in that case if temperature fall, the atmospheric or temperature fall with respect to standard temperature, and therefore the material part A is subjected by tension and material part B is subjected by compression. Like that, if the temperature is raised with respect to its standard temperature, and therefore the material part A now is subjected by compression and part B is subjected by tension. So here we see some general values for alpha, that is coefficient of thermal expansion for steel. So this is the changes happened in the compound bars when it is subjected by thermal stresses. Okay, that one material is subjected by tension and another material is subjected by compression in case of temperature effect in the composite bar. So because alpha value is not constant for the both material, so based on this the stresses are changing. Then for steel, alpha for steel is equal to 12 into 10 power minus 6 per degree Celsius, brass equal to 21 into 10 power minus 6 per degree Celsius, copper is equal to 17.2 into 10 power minus 6 per degree Celsius, aluminum is 23 into 10 power minus 5 per degree Celsius. Yes, next problem solved in this area. A steel rod of area of cross section 200 mm squared is inserted into a copper tube of area of cross section 160 mm squared, and the assembly is inserted inside an aluminum tube of cross sectional area 240 mm squared. Here you see that a steel rod, one material 200 area mm squared into a copper, it is inserted, the steel of cross section is inserted into a copper tube area of cross section 160 mm squared. And the assembly is, these two are assembled and inserted inside the another material aluminum tube of cross sectional area 240 mm square. Here is the Young's modulus of steel is equal to 200 kN per mm square. Then copper, for copper 125 kN per mm square, and E for aluminum is 75 kN per mm square. So this data given. If the assembly is subjected to an total axial pull of 60 kN, determine the stress and force in each of the material. So how many or how much stresses or forces subjected by each material, that thing we are going to find. So cross sectional area of the steel rod 200 and copper tube 160, aluminum tube is 240. So let us find. Axial load is given, E individual material E it is also given. Now sigma C, let sigma C is equal to stress in copper, sigma A is stress in aluminum. Then aluminum, that all three members are joined together, assuming that all three members are joined together, so that the axial deformation is same in all members. Therefore strain in steel is equal to strain in copper is equal to strain in aluminum, which can be written as epsilon S equal to epsilon C is equal to epsilon A, and therefore epsilon S is nothing but sigma S by ES, and epsilon C is equal to sigma C by EC, and epsilon A is equal to sigma A by EA. So all are equating. Now sigma S can be written as sigma S equal to sigma C into ES by EC. Here sigma S can be written as sigma C into ES by EC, like that. Sigma, and let us substitute ES by EC, therefore sigma C becomes sigma S becomes 1.6 sigma C. Like that, sigma AC can also be written as in terms of sigma C, and therefore sigma A is equal to 0.6 sigma C. Now the total load on steel, copper and aluminum PS plus PC plus PA. We know that PS equal to sigma S into AS, that is force equal to stress into area. PC is equal to sigma C into AC plus PS equal to sigma A into A. Now let us substitute all sigma S and sigma A in terms of sigma C, that is copper, and therefore sigma S is nothing but 1.6 sigma C plus, and we know that area of steel it is given, and like that AC area of copper is given, sigma C, then let it be written same, plus sigma A can be substituted as in terms of sigma C, and we know the area of aluminum. So now we have sigma C is equal to this value. Let us substitute sigma C in the above equation, so that we can get the sigma S and sigma A. So from which let us multiply with each area of this material. Therefore we can find what is the force said by each material. That's all.